For local area network LAN links using Ethernet, it is normally not necessary to set the bandwidth manually. However, for serial interfaces, the actual bandwidth should be manually configured because it affects many router processes. For example, routing protocols such as Open Shortest Path First, OSPF, and Enhanced Interior Gateway Routing Protocol, EIGRP, use bandwidth to determine best routes. Bandwidth affects load calculations, quality of service, QoS calculations, and Simple Network Management Protocol, SMMP, reporting. It is especially important to set the bandwidth on non-broadcast multiple access NBMA networks like Frame Relay. Here, the access interface bandwidth and the PVC capacity may be different, and there may also be multiple PVCs on one interface. Actual bandwidth must be the same on each side of the link. Let us now look at the common defaults for bandwidth and delay on Cisco interfaces. You will read the delay in tens of microseconds. A serial interface has a default bandwidth of 1544 with a delay of 2000. For Gigabit Ethernet, bandwidth is 1 million and the delay is 1. For Fast Ethernet, bandwidth is 100,000 and the delay is 10. For Ethernet, bandwidth is 10,000 and the delay is 100. In the next slide, let us look at bandwidth distribution. Bandwidth is distributed differently depending upon the technology used. For multiple cables from a hub, the bandwidth available for each cable is the total uplink bandwidth divided by the number of cables. For multiple cables from a switch, each cable can use the entire uplink bandwidth. In Metro Ethernet, your contract often limits the bandwidth to a certain number below the actual link speed. Let us look at Frame Relay. One PVC is configured for each destination, and there can be multiple PVCs for each physical port. The entire bandwidth is available to each PVC. Let us continue our discussion on bandwidth distribution. For PVCs with matching committed information rates, CIRs, configure the bandwidth to the sum of all CIRs. If the PVCs have different CIRs, configure the bandwidth to the lowest CIR multiplied by the number of PVCs. Example 1. If a T1 access line has 3 256 kbps PVCs and one 56 kbps PVC, the bandwidth should be set to 224 kbps 4 times 56 kbps. It is strongly recommended that you assign the slow 56 kbps PVC to a point-to-point sub-interface instead of lumping it in with your multi-point interfaces. This leaves more bandwidth for the 3 other PVCs. Let us look at an example of longest prefix match. A routing table lookup yields the longest prefix match for the given destination IP address. If the destination address of a packet is 25.25.25.1, which of the routes on the slide will the packet take to the destination address? Click each choice to see the explanation and the correct answer. The destination address of a packet is 25.25.25.1. This address is in the 25.0.0.0/8 network. It has a prefix length of 8. This network also has the destination address and has prefix length of 24, which is a longer prefix match than 8. Hence, this is the longest prefix match so far. The destination address is not in this network, so this route is not in consideration. The destination address is in this last network. So far, our longest prefix match is 24. The prefix length here is 30, which is greater than 24. So this is the longest prefix match. The packet will take this route. Now, let us take a look at the IP classless command. The IP classless command has been the default since iOS 11.3. With no IP classless, if a destination is not found in the routing table, the packet is dropped. With IP classless, if a destination is not found in the routing table, the packet will go to the static default route if there is one. Therefore, to know the default route behavior, make sure you know the iOS version that you are working with. Now, let us review administrative distance.